So Ivan, today we're going to talk about another, possibly one of my favorite techniques. I will introduce you to something called square root decomposition. It's very well known technique for others, so you might want to jump out ahead on the video if you know already square root decomposition. But even if you know, you might learn cool things and the proof is just very intuitive, I would say. Let's imagine that we have some kind of an array. So these are some numbers. We don't care really about the numbers. We just want to do some queries on some ranges. So we want maybe to sum up some number here, some numbers of from this point to this point. And now we can forget about techniques that are like prefix sum and segment tree and fanfic tree. We can forget all about these techniques. I don't care about these techniques. I want to show you why square root decomposition actually works first, right? So first, what we're going to do is, given this here, I will divide it into some blocks. Let's say somewhere I will divide it somewhere like this, into blocks like that, okay? And now what you can see is that for some blocks, this block here is in the whole as a whole, it's in the range that I'm querying at. So this block, if I somehow know the sum of this block, let's say this is 10, if like this is 2, this is 2 and this is 6, let's say, it doesn't matter. If I know the sum of this block, I can quickly say, oh yeah, this block contributes to the answer with 10. I don't care about the numbers inside the block, okay? But now we have left over something here. Some numbers from the left side and from the right side. And now I claim like this. If we have n elements into the array, right? So we have b blocks, and we have n divided by b of these elements here. And I claim that for each query, we can have at most b blocks that we can iterate, and they are all inside of the query. So we can have all of the blocks are inside of the query, so in the question range, right? Or we can have some blocks, but then there maybe are n divided by b blocks that we need to individually iterate and sum over, because this block is not really the whole in the range, you know, like it's only these elements we need to take a look into, right, to sum up. So I claim that at the worst case scenario, we have something in the order of all of this. So we have some n divided by b blocks that we need to iterate over here, right? And this might be two times because of one side plus other side plus b blocks that we may iterate. But this 2 is a constant. We don't really care about constants right now. We care about this equation, 2n divided by b plus b. So what is the most optimal value of b, I would say like this. To make it as faster as possible, I need to choose a value such that if I choose a lot of blocks, I will have this here b. It will be very, very big if I choose this a lot of blocks. Okay, this will be small, but this would be very big. If, on the other hand, I choose a small amount of blocks, right, then this would be very big. This would be close to n. And now somewhere I need to find an integers. I need to find some integer that would be the most optimal way. And we can pretty easily claim without really rearranging this, even if we rearrange this. And I claim that if I choose that b is equal to square root of n, if I exchange here, it's like n plus the square root of n squared, right, divided by the square root of n. which in turn will say that n plus n, right, divided by the square root of n, which in turn is 2n divided by square root of n, and this is square root of n. This is equal to square root, 2 times square root of n, right? So 2 is a constant, right? We can just pull that over, right? But we now know that square root of n, if you graph this function, you will see that square root of n is the most optimal. It's actually pretty helpful not to choose square root of n in contests and to choose somewhere close to square root of n. So try out a constant, so some constant less or more than the square root of n. Why am I saying this? Because many of the judges, when they're creating these problems, they already know about square root decomposition. And what is the idea here? The idea maybe is to generate tests which for some exact b, your solution will fail. So if you choose exactly square root of n, there may be a test case where your solution will fail. But if you choose -1 or +1 or -10 or -15, some random value, it's very, very likely they didn't construct a case for each of these individual sizes of blocks, so like the number of blocks, right? So what I want further on is to show you a problem from CodeForces, from a recent CodeForces round, that kind of elevates this technique. So the problem is as follows. You are given some tree. So you have some huge tree. And the constraints on the tree were n went to about 10 to the 5, I think, and there were Q questions, Q queries, which also went about 10 to the 5. And each question was a really interesting thing to do. You had to do. And it was this. You were given two nodes. Let's say that you're given this node here and this node here. So you were given some U and V nodes. And then these nodes were guaranteed to be on the same depth, right? And what you had to do is to find this interesting kind of sum here. So what you had to do is you had to make the product of these values that are here. So here this value is, let's say, A of U and this is A of V, right? Let's say like this, A of U times A of V, right? And then both of these, you move them to the parent node. So you somehow move yourself, not the nodes, but you move yourself to their parents. And then you sum up their product. So the parents' product have some parent, whatever, it was some A of W times A of W1 or whatever, A of WU, A of WV1, I don't know, like it doesn't matter. Then you sum up plus A of W2, A times A of WV2, right? And you went there until you went down to the root node. So you had this enormous thing you need to do. So you need to go like this, and product of this plus product of this plus product of this plus product of this plus product of this, right? You had to do all of these steps. And now you can probably imagine if I had a really long tree, right? So if I had like really long tree here and I had like some other here thing really long, right? Then I would need to do all of these steps like that, all the way up to the top. Even though, okay, here now they match, and now we can say, okay, this we already maybe pre-computed or whatever. But let's say you have to do at least to here, right? Which could be in order of n divided by 2, let's say. Really, you could have really long tree, and you could have questions about nodes on the bottom of the tree. And now to solve this problem offline is of course possible, and there are some solutions. Maybe most of the people solved it online. I'm not pretty sure. Offline, not pretty sure, but offline is just sorting out how the queries. Sorting out the queries and then answering them cleverly. But we're not going to discuss this solution. We're going to discuss a much more clever solution, and that way that you can solve it online, you can write it really fast, and it's really intuitive. And the solution is the same idea as we did with the blocks, but instead of blocks, what we're going to do is we're going to divide the tree into b depths. So like we're going to divide the tree on every b here depth, on some like n divided by b depth. So if they are like n or maybe we're not going to do this. We're going to divide the tree by some b. We're going to divide the tree such that every b depth, so every node here, we're going to do something special. And after that, we're going to wait for b nodes, and then we're going to do something special again. And then again, the b here, I claim that it's really good to pick square root of n. And I will prove why this actually works and why this actually doesn't work in a very special case. But this case can be avoided by picking either a really like randomly b, so like changing the b a little bit random, or by picking or by just creating dynamic choosings of these b. But this is far you don't really need this. You will pass the cases even if you don't do that. For each of these b nodes here, there might be so there will be square root of n of these nodes here, probably like levels. So there could be like levels here, there could be levels here. It doesn't really matter. Okay, but after on this depth, we are going to make this level a special level. This depth here, these nodes that are on this bth level they're going to be special nodes. And what we're going to do is we're going to try on these special levels, we're going to have pre-computed for each pair of these nodes that we can come to, right? We will have pre-computed the answer. And why is this very clever? Okay, let me show you why. Let me really show you why is this very clever. So let's imagine that these again are the two nodes, right? If I have computed here the answers, and if I have computed here the answers, when I will come to here, right, I will already know the answer. How many steps in the worst case I will take until I reach some of these special layer here? How many nodes would I take at the worst?
Well, I would say b steps.
Yeah, exactly. So like, because every b steps I have this special layer. So okay, so we say to answer a query, we will have b steps. So b, we said a logarithm of n, right? A logarithm of n, square root of n, right? Square root of n is a very small number compared to n, and in most cases it will pass, right? But now we have one major problem here. One major problem is the following. First, we have to decide which of the layers we are going to make special layers. Because imagine the following structure. Imagine if I make a layer such as these with full of nodes, I make special layer. Now, a layer full of nodes might have n nodes, or n divided by 2 nodes. And now, if I have n divided by 2 nodes, right, and I try to make this special layer, I need n divided by 2 squared calculation, n to the power of 2 divided by 4 different pairs that I need to compute for such a huge layer, right? But now we can further change a little bit our argument. We're not going to pick any of these layers. We are not going to make so we have here, I said after B nodes we're going to make a special layer. No, we will redefine this. We will say in every B depth, so in every node, B nodes here, I will pick the layer which has the least amount of nodes in it to make this a special layer. Why the least amount of nodes in it? Because this number here will be very small. So the pairs, if you have something in order of square root of n, right? When we do the squaring afterwards, it comes around n. So we can afford n because we will have square root of n levels, right? And we're going to pick a very efficient layer in each of these levels, and this will be at most n. I claim that this will be the complexity of the precomputation. But how will you prove this, and actually how would you disprove it if you are not careful in constructing this square root decomposition on a tree, right? So I will try to construct a case where this will fail, right? But first I will just show a general construction. I want in every of these B points here, I want in every of these B depths that I'm going to choose, in every of these B depths, I want to have the most unoptimal thing, because if I choose if I have something that is smaller than the most unoptimal thing, I will choose this, right? If I have a layer which has smaller amount of nodes in it, I will choose that layer. But I want to make all of these layers very big, right? To make it as hard as possible to pre-compute. Okay, so we will have here we will have of a depth B. So this we know that is square root of n, right? And for each of these, if I want to make it full layer, so full nodes, right? How many nodes would I maximally can put in this layer? So I have square root of n layers. I have at most 10 nodes. How big one layer can be?
Well, square root of 1.
Yeah, exactly. So square root of n. So square root of n can be all of these layers must be square root of n in order to make this possible, right? So we prove that in every layer we will have square root of n. But we said for calculational purposes, we need square computation per layer. So if I have square root of n here on one layer, for calculational purposes, I actually need square on that, right? And this is still n. Excellent. So we prove that because for each pair of some layer here, for each pair of this layer, we will have at most n pairs, because we have square root of n nodes in that layer, right? So we prove that in this block case, this case where I have square root of n and square root of n, right? I can do the precomputations. So I can do the precomputation. But there is a case where, imagine this. So I have some nodes like that. And then here at the bottom, I have chain of nodes. And I claim that maybe I will construct a case such that these nodes will be really tall. So I mean, not really tall. This will be exactly b, so square root of n tall, right? And if these are exactly b tall, then here what I will get, so exactly with that node here, so with that node, I will get one layer here in the next section. I will get one layer which has n minus square root of n nodes. Right? Is this follow? Because I have square root of n here nodes. In this layer, I will have n minus square root of n nodes. And this is really bad. Because if I say that this is a special layer here, if I say this is a special layer here, and if I say that this is a special layer, right? Because in this range, I pick this as the smallest layer possible, right? So this is the smallest layer possible, and I make this a special layer, and I compute for this, right? Then for these here, I'm left with to pre-compute for this layer. But we said that this layer has n minus square root of n nodes, and when I compute that, it's squared, and this is actually in order of n squared. And this is why you have to be careful about these edge cases. These edge cases can be constructed for a very specific n. So instead of square root of n, you can make it square root of n plus minus something in order to avoid these edge cases, the judges that can construct. This is the whole idea of square root decomposition on trees. The whole idea is just to break down the tree into blocks and to compute this optimally, so on optimal levels to pre-compute this, because you don't want to compute on very dense layers. You want to compute on very sparse layers something. This is actually used in many tricks, even tricks with string matchings. This is used. So if you don't know how to solve a problem with segment tree or with heavy light decomposition or with century decomposition on a tree, you may want to try to divide the tree into blocks and pre-compute some other special nodes in these blocks. So you don't need to have like whole layers pre-computed. You could have like somehow special nodes that will tell you something pre-computed, and then you can just go to that special node, just run around the tree, go to that special node, and then you'll have the answer. So it's a kind of really interesting technique, and I hope more problems are created on this specific technique, because not all of the problems can be solved with segment tree or heavy light decomposition. So yeah, thank you guys so much for watching, and I see you in the next one.